This conference will now be recorded.
So, very good evening. We had started with this chapter Semiconductor Electronics, Materials, Devices, and Simple Circuits. We had already learned about the introduction of this chapter. We have discussed already vacuum devices. Then we have seen the advantages, disadvantages of vacuum devices, diode, threads, etc. We have seen, and then we have understood that semiconductor solid materials are more advantageous, which allows us to control the flow of electron or the charge carriers very easily. Okay, and then we have discussed, depending on the value of resistivity, how many classifications, like how many divisions of materials are there. We have learned insulator, metal or conductors, and semiconductors. So today we'll be basically learning what is energy band, and we'll see how do we classify materials on the basis of energy bands and how many different types of materials are there. And if time permits, we'll start with extrinsic and intrinsic semiconductors. So let us learn first what is energy band diagram. So basically we'll be discussing energy bands for silicon and germanium. Let me tell you first very general idea of energy bands. So we have learned in atomic or atom chapter about Bohr's atomic model, and you can see this is the structure of Bohr's atomic model, where the nucleus is at the center, and keeping the nucleus at the center, electrons are orbiting in various orbits. So this is the case in case of this is actually a single atom or isolated atom. Isolated atom. Isolated atom in the sense it is very far from any other atoms. Okay. So in case of isolated atom, the energy of any electron depends on in which orbit they are situated. We know energy En is equal to minus 13.6 by n square for hydrogen atom. If it is not hydrogen, if it is hydrogen-like atom, then z square by n square will come. Okay, and this is electron volt. And since this is a quantum number, so energies are actually discrete. So we have various energy levels. We have seen in the chapter atoms. Okay, so we have the lowest energy like this, minus 13.6. Then we have energy. So if we divide this by 3.4 electron volt with the minus sign, and then like that, various energy levels we have seen, and at very large, at n is equal to infinity, when it goes n is equal to infinity, energy levels are continuous, or there is no isolated, like these are. So So these are the states for bound electrons. The energy levels are for bound electrons when they are bound to particular orbit. And when n is equal to infinity, that means electrons are very, very far from nucleus and they are not bound further. They are free to move anywhere. So this is called actually conduction level, or this is actually ionization or ionization. This is called ionization levels. And here electrons are free. Electrons are free to move anywhere. Okay. So my point is that energy of electrons in isolated atom depends on the fact that in which orbit they are situated. Okay. But when we want to make a solid crystal, then we don't have a single atom. We have of the order of n. Maybe it goes up to at least up to the Avogadro number 10 to the power 23 atoms. Okay, we have much more than that. So we have many atoms together to form a solid. Okay, many such atoms are coming together to make a solid material. Okay, and when various atoms are coming close together, then what happens? The energy of the valence electron or atom of electron actually get affected by the presence of all other atoms, because in that case, suppose this is only one atom. If I take similar another atom over here, so it has electron over here, this is nucleus and many other electrons like that. Okay, so this is the outermost electron here, and this is for this atom, this is the outermost electron. So these two electrons will come very close to each other in the solid. Okay, very close to each other, or sometimes they may overlap also. So because of that, there will be an interaction that is called actually electrostatic interaction, Coulomb interaction. Okay. Not only that, since there will be the atoms very close to each other, the electron can interact with the ion cores also, positive ion cores nearby. So you have electron-electron interaction, and you have electron and proton or the nucleus interaction. Okay, I'll say plus. So these interactions are there, and when there is such interactions among the electrons or between electron and the ion cores, then the energy of this isolated, like this outermost electron, will be affected. And see, when in the solid there are atoms close back, and see in the crystal, each electron will have unique position. In crystal, there will be many such atoms, and each electron will have unique position and unique surroundings. That means the interaction at each and every point will be different. And because of that, the like each electron will have different energy. Each electron will have different energy. So like see, each electron has some discrete energy level. That I agree. So, but now, even though these atoms are identical, but the situation or the environment of this electron is not same as this electron. Just for this electron will be having different energy. Suppose it has here, and some other electron will be having here an energy level. Some other electron will be like here. So there will be, you will see there will be a continuous variation of such energy levels. So you will have innumerable energy levels, or many energy levels with a continuous variation of energy. Therefore, if you have very close lines from each other, very close to each other, then there will be actually a continuity in the energy. There will be no longer discrete energy levels like this and this. So there are levels in between also. So these various levels, continuous variation of these levels will form a band. So this is called, these are called energy bands. Okay. So we have seen that different discrete levels with continuous variation form a band called energy band. Okay. So this is how they form an energy band when isolated electrons are coming closer to each other. Then the atom of electron will be interacting with neighboring electrons at ion force, a positive force, and therefore its electron will be getting affected, and there will be many electrons in the solid. So many electrons will be having many discrete levels of energy, and those discrete levels will come very close to each other and form a band like this. Okay, but this formation of band depends on the distance of the atoms. Generally in solid, the atoms will be hardly 2 to 3 angstrom away from each other. That means very close to each other. Now we'll take up two materials, silicon and germanium. For them, we'll specifically learn the formation of energy band. Okay. Let me tell you here itself, there are two kinds of bands. One is valence band. Okay, valence band. This includes the energy level of valence electron, and there will be another band that is called conduction band. Conduction band. So this band includes the energy levels of conduction electrons. Okay, conduction band includes the energy levels of conduction electron, and valence band includes the energy of valence electrons. So that's how two bands will be formed, and sometimes there will be a gap between valence band and, and conduction band, and sometimes they may overlap. That depends on the material, like whether it is metal, insulator, or semiconductor. Depending on that, is there will be a gap or no gap between these energy bands. Generally, conduction band is having higher energy, and valence band has lower energy. Okay, we'll move on to the next slide. We'll see here. This is a very technical energy band diagram. This looks very horrible, and maybe you might be thinking it is very complicated, but as we discuss, you will understand. So what we will do, we have silicon and germanium. We know silicon, how many electrons they have? They have 14 electrons, and if we write the energy, sorry, electronic configuration, then it is neon 4 with 3s2 and 3p2. That means it has valence electron in the n is equal to 3 level. Okay, so the principal quantum number is 3. So it has valence electron, 4 valence electron. So how many electrons are there? Okay, so how many electrons are there? There are 4 electrons, 4 valence electrons. Valence electron. Okay, and how many levels are there? How many energy levels are there? There are 4 electrons. There are 6 levels. So 6 plus 2. So 8 available energy levels are there. Available energy levels are there. Now, if we just consider germanium, actually they have similar crystal structure. Let us see the configuration, electronic configuration. It has 32 electrons. So if we see the configuration, electronic configuration, so it will be having so argon 18 closed cell, and along with that there will be 3d10, 3d10. That means it is completely occupied, and 4s2 and 4p2. So here the electrons are there. Valence electrons are here in the 4s and 4p. So here also s and p. So you can see there are 4 electrons, 4 valence electrons, and 8 available energy levels. Energy levels are there. Okay. So what does this mean? 4 electrons but 8 levels. Yes, we'll see it carries a very significant concept. See, when an atom is isolated, that means one atom is far from the other. So such cases in isolated atoms, see these 8 levels, total 8 levels are there. There also total 8 levels are there. But all the levels will be having the same energy. Look here, L is equal to 0. That means it has S cell, and this is L is equal to 1 corresponding to P cell. So in the P cell there are 2 electrons, and in S cell also there are 2 electrons. Look, one thing here, if I have n such silicon or germanium, then I will have 4n number of valence electrons. 4n valence electron and 8n available energy levels. Okay. If I have n number of atoms, then 4n number of valence electrons and 8n number of available energy levels will be there. But these 4n electrons, some of them like 4n, 2n electrons will be there in the S cell and 2n electrons will be there in the P cell. So all 2n electrons in the P cell have the same energy, even though there are 6n states in the P cell, and there are 2n states in the S, but all S. So 2n means you have many energy states, but they are having the same energy. These are called degenerate levels. Okay. All P's are having same energy, all S are having the same energy. So in the beginning, you look 2n electron S and 2n electron will be there in the 6n step. So 2n S step and 6n P step. So this is the case when it is isolated atom. You will have discrete energy levels, and all 2n or all 6n P state or all 2n atoms closer and closer. This is the region A, which is isolated atoms. Now, if you bring the atoms closer to each other, then what happens? As I said, the atomos electron will have like their energy levels will be getting affected. These 6n states and 2n 6n P state and 2n A state. Obviously, P has high energy. So these P states and N states will be getting separated. You look, there will be 6n p steps which has higher energy. At the same time, there will be 2n electrons in the p. So this is called p band. This is p band, and this is s band. Okay. So in the s band, there are 2n electrons, and in the p bands also there are 2n electrons, and there is a gap between p band and s band. So p band is called actually conduction band, and this is called valence band. Further closer to each other, look here in the C region C. In this region, so there will be this discrete levels are forming a band, but these bands, whether they will be separated from each other by a gap or they will overlap each other, that will depend on the distance, interatomic distance. See here, interatomic distance is this one. So in this region, actually there is a gap existing between 6n p states and 2n s states. But as you bring further closer, then we reach this C region. You look where the lowest level of the higher energy band is lower than the highest level of the lower energy band. This is S band, higher level of the S band, and this is the lower level of the P band. That means they overlap each other. So in general, when there is a gap between this level and this level, two bands, then the electrons in the lower band will not be able to move to this higher band because there is an energy gap. Unless and until you give sufficient energy to the electrons over here, to reach to conduction band. Okay, and in general, if you apply some light or electricity or whatever, there are many such external excitation by which the electrons in the valence band can be excited to conduction band by supplying certain energy. Okay, but in general, conduction band will be empty and valence band will be completely filled. Now, if these two bands are overlapping each other, then electron from the lower level can easily move to the higher level, and this is the case for metal. We will see that. Now, if you further decrease the interatomic spacing between the two atoms or the atoms, then what happens? You will see further there will be the energy band will split into two. Okay, 4n. See here, it was here 6n states were there at the upper level and 2n states were there in this. But in this case, what happens? Even at very low atomic spacing, there will be two bands. One is upper band, another one is lower band. These are truly called valence band and conduction band. And these bands will be actually having available energy states 4n and 4n. Both the bands will be consisting of 4n energy.
Ram, no sound. Ram.
Is it okay now? Is it okay? I don't know, something happened. It is okay, right?
Now it's okay.
Okay. So what I was saying that initially you have seen that there will be two bands formed. One will have 6 energy levels and another one will have 12 energy levels. But as you decrease the interatom spacing further, then you will have two bands again with like one will be higher band, another one is having lower energy band. Lower energy band is called the valence band, and the higher energy level is will be having 4n equal number of states. Okay, equal number of states are available energy levels 4n and 4n. But in this case, what happens? All the electrons, 4n electrons will be there in the valence band, and there will be no electrons in the conduction band. So conduction band generally becomes empty, like remains empty, whereas valence band remains completely full. Okay, completely filled. And there is a gap, energy gap, that is called band gap. Easy. We'll see that. Okay. So this is how energy bands form. And see, depending on the various pattern of this, and okay, so this is the schematic diagram of the band structure of any material. Okay, this is how we will be drawing the band. This is actually conduction band at absolute zero temperature. At absolute zero temperature, conduction band, which is 4n states, will be empty. As you see, all the energy, so there are 4n energy levels, and all the levels are empty. And whereas this is called valence band, 4n states are there, and all the states are completely filled with electrons. Conduction band, and the lowest level, energy level of the conduction band is denoted by EC. EC. Okay. Lowest level of the conduction band is denoted by EC, and highest level of the conduction band, sorry, valence band, highest level of the valence band is denoted by EV. Okay, EV. EV for the highest level of the valence band, and EC lowest level of the conduction band. Now, whenever we do calculation of band gap, we'll just take the difference or gap between these two, EC minus EV. This will be giving you the energy band gap. Energy band gap. This is called energy band gap, generally denoted by EG. So EC minus EV will give you energy band gap. Okay. So this is the schematic diagram of energy band diagram of any substance, or for this absolute zero temperature. Absolute zero temperature, what happens? No electron can have sufficient energy to move from valence band to conduction band at this low temperature, absolute zero temperature. But if see some cases of material at room temperature, the electrons from valence band can gain sufficient energy to move from conduction band to valence band to conduction band. Okay, and when this happens, the electrons in the conduction band will move freely and contribute to the conduction process. And in the valence band, when one electron just moves to conduction band, it will create a vacancy over here, and that vacancy has effective positive charge, and that also will move between all four energy states, and then movement of that positive vacancies also will contribute to the conduction process. Okay, electric current, etc. it will provide, like it will produce. Now we'll classify materials on the basis of energy band diagram. So we have general idea about energy band diagram. This is valence band and this is conduction band, like this, and this is valence band. Okay, and there is a gap. This is EV, this is EC. Okay, and there is a gap EG. Like that we can draw wherever and whenever required. So look here, I have two figures and figure 2. If we look here, these two figures, look, this is conduction band. It is shown here. This is conduction band, and this is valence band. One interesting point you look here. Generally, at room temperature, conduction band should be empty, but this is partially filled. Partially, or we say partially empty. No, we should say partially filled. So conduction band, this is actually filled. This much is filled, only this much is remaining. The conduction band here is partially filled. Okay, partially filled conduction band. Filled conduction band. And see, in the valence band, generally it will be completely filled, right? But see, this portion is empty. So we say valence band is partially empty. Partially empty. Empty. So when such things happens, you have some electrons already in the conduction band, so you will get electric current. It will actually conduct electricity. Okay, it will conduct electricity. So therefore, it will be actually a conductor. It will be a conductor because you have already electrons in the conduction band. So this is the nature of conductor. When any material has this kind of energy band, partially filled conduction band and partially empty valence band, then see in the valence band, you know, the valence band, electrons can go to this vacancy level, leaving a hole. That hole will move to the next level. Like that, holes also will be contributing to the conduction. And these electrons, you have three levels there. So you have electrons, they can move around and they can contribute to the conduction process. So this figure 1 is actually for metal or conductors. We'll see another point for like another type of band diagram for conduction band. See, in conductor, sometimes the lowest level of the conduction band, PC, will be having energy lower than the highest level of the valence band. And in such case, conduction band and valence band, they will be overlapping each other, right? We have seen that. So they will be overlapping each other. Okay, you look here. The lowest level of the conduction band is here below the highest level of the valence band. That means what? Valence band and conduction band, they overlap. Overlapping conduction band and valence band. And in such case, you know, whatever electrons are there in the valence band, they can easily move to valence band, sorry, conduction band, and take part in the conduction process. So in this case, Eg is 0. See, Eg is 0, band gap is 0. So this is the characteristics band diagram, energy band diagram for metal or conductors. So in case of conductors, either there will be partially filled conduction band and partially empty valence band, or conduction band and valence band, they will be overlapping each other, so that all the valence electron can easily move to the conduction band and take part in the conduction process. That's why the resistance or resistivity is very less for conductors, because the band gap is very less, nearly equal to 0. Okay, so that's why resistance is very less. They can take part in the conduction process very easily. So these one and two. These are actually band diagram, energy band diagram for energy band for conductors. Okay, we have learned conductors. Let us learn about insulator. So in case of insulator, what happens? The conduction band is completely empty. See, this is the case. This B, the figure B, depicts that completely empty conduction band and completely filled, and there is a band gap. And what is the value of this band gap? Greater than 3 electron volt. And this is huge energy gap actually. So if you have a material which has conduction band and valence band separated by an energy gap more than 3 electron volt, so such materials are called insulators, because you don't have electrons in the conduction band, and hence there are no possibilities of conduction of electricity. At the same time, even if there was a possibility to populate this conduction band by valence electron, but the band gap is so large that it will not be possible to excite any electrons from valence band to conduction band, and that's how it will act as an insulator. Now look at this figure. This figure C. In this case, there is a band gap between conduction band and electron like valence band. There is a band gap, but the band gap energy is less than 3 electron volt. This case, actually, these are the materials, semiconductors. Okay, for the materials, for like the materials which have conduction band and valence band separated by band gap energy less than 3 electron volt, then that is called semiconductor. In case of silicon, actually it has Eg almost 1.1 electron volt, and for germanium it has even less, nearly equal to 0.7 or something electron volt. It has very less band gap. Okay, so it is, at least we can say that the band gap Eg is less than 3 electron volt, then those materials are called semiconductor. So this is a very important question for board exam, and for understanding also it is a very important thing. So today we'll stop it here with this. Next day we'll learn about intrinsic, extrinsic semiconductor, and formation of holes, electron, and all those things will be learning. And also we'll try to cover the p-n junction part also. So next day we'll learn what is called extrinsic and intrinsic semiconductor, what is called p-type semiconductor, p-type and n-type semiconductor, and when p and n make a junction, that is called p-n junction. We'll try to learn how p-n junction is formed and what all physics is there at the p-n junction or at the junction. We'll learn in the next class. So Deepa, if you have any question or doubt, or anything, you can ask me now. Do you have anything to ask? Okay, then we'll stop it here for today. We'll meet again on Sunday, discuss various things about semiconductor, P type, N type, semiconductor, etc. We'll discuss on Sunday. Okay, so bye for today.